up, everybody? This is Tech G back with another video. And in this video, we're going to be talking about the structure of machine learning models as it relates to artificial intelligence. So let's get into it. Let's say you're scrolling through your favorite streaming app. You watched a few rom-coms last week, and suddenly it's suggesting a dozen more. Now, is this magic? Not exactly. That's machine learning doing its thing behind the scenes. But how does it actually work? Well, this is going to be your deep dive into the structure of machine learning models, which are the inner workings that power everything from recommendation engines and facial recognition to language translation and self-driving cars. And in this video, we're going to break it down step by step. We're going to talk about what features and labels are and why they matter, what training data is and how models learn from it, and then how we evaluate if a model is actually doing its job. So I'm going to try to make this as pain-free and practical as possible. So with that being said, let's get into it. All right, so first things first, we need to identify exactly what is a machine learning model. So imagine you're trying to teach a dog new tricks. You give it a command like sit, you show it how to sit, you give it a treat when it gets it right, and then after enough repetition, the dog learns what sit actually means. A machine learning model is a little like that dog, but instead of learning tricks, it's learning patterns from data. You give it a bunch of examples, which are called training data. You tell it what the correct answers are, which are known as labels, and it adjusts itself internally to get better over time. Eventually, it can make predictions or decisions based on new data it hasn't even seen before. Now, with that being said, let's go ahead and explore each part of the process in more detail. All right, so first up, let's talk about features. Now, you could think of features as the information you give to the machine learning model to help it make a decision. It's like the ingredients in a recipe. Without them, the model can't cook up any results. And here are some examples of features. So let's say you want to build a model that predicts the price of a house. Here are some features that you might use. You could use square footage, how many bedrooms does it have, the number of bathrooms, the zip code, and the year the house was built, in addition to how big is the lot size. Now, each of these things is a feature or a data point that helps the model understand what might influence the house price. And when it comes to features, here are some feature types. So features, they could be numerical, like age, income, or temperature. They could be categorical, like color, gender, or zip code. They can be in Boolean, where they represent a true or false, or a yes or a no. Or they could be textual, like reviews or comments, where a comment might say something like special handling. Now, as a pro tip, choosing the right features, which is called feature engineering, this is one of the most important skills in machine learning because bad features can produce a bad model. All right, next let's talk about labels. So if features are the ingredients, then labels are the final dish you're trying to make. In machine learning, a label is the value or category you want the model to predict. So here's some examples of labels. So using our house price example, the label is the actual sales price of the house. Also, another example, if you're training a model to recognize spam emails, the label might be spam or not spam. And another example could be if you're training a model to recognize cats in images, the label is either a cat or not a cat. And then we have what is called supervised learning, and this is features plus labels. So most machine learning models, especially in beginner level projects, they use something called supervised learning, where the model learns from both the features and the correct answers or the labels. Now, the idea is simple. You show the model examples and the correct labels, and it will learn to predict the labels from the features. All right, so let's talk about training data. So you've got the features or the input and your labels, which are the output. Now you need to connect the dots, and that's where the training data comes in. So exactly what is training data? Well, training data, this is the collection of examples the model uses to learn patterns. And each example includes both features and a label. So let's go back to the house price example. Your training data might look like this chart on your screen right here. And in this chart, the model analyzes these examples and learns how the input features relate to the output price. And over time, the model updates its internal math, which is called weights and biases, to improve its predictions. So remember in this example, square feet, bedrooms, bathrooms, and zip code, all of these are features. Your label is the price. So all of these features are going to help determine what the actual price of each house is. All right, so next let's talk about testing and evaluation. So your model has been trained. Now what do? Well, you need to evaluate it. Basically, you're testing how well it performs on new and unseen data. Now, why are you doing this? Because we don't want a model that just memorizes the training data. We want one that generalizes to new examples. And how do you do this? Well, the first thing you're going to do what is called splitting your data. Now, most machine learning workflows, they involve splitting your data set into training sets, and that's usually about 70 to 80% of the data, and this is used for training the model. And then the other 20 to 30% is called the testing set, and this is used for evaluating performance. Now, sometimes there's also a validation set, and this is used to fine-tune settings before the final test. Then after you do that, you're going to make predictions on the test set. So now the model makes predictions using the features in the test set. Then we compare those predictions with the actual labels in the test set. And then we use evaluation metrics. So basically, how do we measure whether the model is good? Now, this depends on the kind of task you're doing. And we're going to go ahead and explore some of those common types. All right, so let's talk about evaluation methods in machine learning. And the first type we're going to talk about are for classification problems. And you can use this for spam and not spam type of examples. And your common metrics include the following. You have accuracy, and this is the percentage of correct predictions. This is simple and intuitive, but it's not always reliable, especially for imbalanced data. Then we have what is called precision. So of all the positive predictions that the model made, how many of them were correct? Now, this is good when false positives are costly, like predicting diseases. Another metric is called recall. So out of all of the actual positives, how many did the model find? Now, this is important when missing a positive is dangerous, like detecting fraud. Then we have what is called the F1 score, and this is the harmonic mean of precision and recall. Essentially, this balances the two, and this is great when you need an overall performance metric. And then we have what is called a confusion matrix. And this is a table that shows true positives, false positives, true negatives, and false negatives. Essentially, this gives a deeper look into how the model performs. And then we have some other types of evaluation metrics that are known as regression problems, and these are good for predicting house prices. So essentially, you're predicting a number instead of a category. And the first type is called the mean absolute error. And this is an average of how far off predictions are from actual values. You have what is called the mean squared error. And this is like the first one, but this squares the errors before averaging. And this essentially penalizes large errors even more. And then we have what is called the root mean squared error. So this is just like the square root of MSE, but this puts the error back into the original unit, like if we're dealing with dollars. And then you have the R squared score, or the coefficient of determination. And this measures how well the model explains the variability of the target. And a score of 1.0, this means a perfect prediction. Now understand, I'm just giving you a high level overview of what this stuff is. We're not going to go into extreme detail with this. Now let's go ahead and tie all of this together with a real world analogy. And that analogy is going to be teaching a child to read. So step one, as it relates to features, this is when you show the kid flashcards with letters on them, and the letters are the features. Then we have labels. This is where you also tell the kid what each word is supposed to sound like. And once again, these are the labels. Then we have training. So this is when you go through hundreds of flashcards together. That is your training data. Then we have the evaluation. So later you test the kid with new flashcards to see if they can still read correctly. You evaluate how many they got right, how fast, and whether they struggled with certain letters. These are the evaluation metrics. And basically, that is machine learning in a nutshell. All right, so congratulations. You now understand the basic structure of machine learning models. This isn't just geeky knowledge for coders or data scientists. It's foundational for anyone who wants to understand how AI works, make better use of smart tools, or even pursue a career in machine learning. So whether you're trying to build your first model, you're trying to understand how AI makes decisions, or you just want to explain this stuff to other people, this knowledge gives you the power to do that. Now just remember, AI models, they're only as good as the data that we give them and the way we measure their success. Now, with great data and great responsibility, we can build systems that really do make life a whole lot better. Now let's move on to our favorite section, and that is the check on learning. So our first question is, what are the features in a machine learning model? Is it the final outputs a model predicts after training? Is it the columns of data that represent input variables that are used to make predictions? Is it the labels that are assigned to each data point? or is it the functions that are used to train the model? And the correct answer is it is the columns of data that represent input variables that are used to make predictions. So features are the individual measurable properties or characteristics of the data being used to train the model. In a spreadsheet analogy, they're the columns that describe aspects of each row or data point, like age, height, income, etc. Next question. Which of the following best describes labels in supervised machine learning? Is it data points that are used only during testing? Is it human assigned tags for model explainability? Is it functions that adjust the model's parameters? Or is it known outputs that correspond to input features and are used to train the model? And the correct answer is it is known outputs that correspond to input features and are used to train the model. So labels are the correct answers the model tries to predict during supervised learning. So for example, if you're building a model to predict whether an email is spam or not, spam and not spam are the labels. And our final question, which method is commonly used to evaluate the performance of a machine learning model? Is it training the model on new unseen data? Is it measuring the number of features in the data set? Is it splitting the data into training and test sets and using metrics like accuracy or precision? Or is it counting how many labels were assigned manually? And the correct answer is it is splitting the data into training and test sets and using metrics like accuracy or precision. So, to evaluate a model's performance, data is typically split into training and test sets. After training, the model is tested on the unseen data, and metrics like accuracy, precision, recall, and the F1 score are calculated to determine how well the model performs.